So 30,000. I really want you to hold that staggering number in your mind for just a second. We aren't talking about a distance here or a temperature. We are talking about 30,000 individual, dense, cometary knots suspended out there in the deep freeze of space, all swirling within one of the absolute most famous cosmic structures in our entire sky. Welcome to The Explainer. Today, we are locking our cosmic focus onto Caldwell 63. You probably know it better as the Helix Nebula. Located about 655 light-years away from us in the constellation of Aquarius, this planetary nebula is just an absolute architectural marvel. It's actually one of the closest of its kind to Earth, which makes it this spectacular front-row laboratory for us to understand the life and death of stars. But, as we're going to see, the popular photos we all know and love, they actually hide an incredibly complex, multi-layered, three-dimensional reality.
Okay, let's dive right into our macro to micro flight plan today. First, unveiling the bipolar barrel. Second, the chemical fingerprint. Third, the cosmic lava lamp. And fourth, a swarm of cometary knots.
Section 1. Unveiling the bipolar barrel and getting a look at the true shape. All right, we need to prepare ourselves to bust a pretty famous optical illusion regarding what we're actually seeing when we look at the Helix Nebula. For the longest time, the scientific consensus leaned hard toward the tilted disk model. Basically, this idea proposed the helix was essentially a flattened disk, maybe 0.33 parsecs thick and tilted roughly 21 to 30 degrees relative to us. And you know, that made total sense based on older two-dimensional images. But modern high-resolution mapping of molecular gases, specifically looking at molecules like HCO+, has literally revolutionized our understanding. Enter the bipolar barrel model. Turns out, the helix isn't a flat disk at all. It's actually a bulging, thick-walled cylinder. A barrel, basically, tilted just about 10 degrees east and 6 degrees south relative to our line of sight. So the really crucial takeaway here is that those iconic rings we see in all the photographs, they're an artifact. It's an illusion created by this massive 3D barrel being projected onto our 2D view of the sky.
Let's ground this in some hard data, because the scale we are dealing with here is wild. We've got our main barrel with its slight tilt, right? But then we also have these high-velocity, highly collimated plumes shooting out in a northwest to southeast orientation. These plumes have literally punctured holes right through the walls of the main barrel. And wrapping around all of this chaos is the extended halo. Check out that value at the bottom. It has a massive 1.2 parsec radius. That is an immense outer shell dominated by thermal emission from warm dust, which goes to show that the true boundaries of the helix extend way, way beyond the bright, colorful inner region we usually focus on.
Section 2. The chemical fingerprint and a very stark chemical divide.
So, what we find inside the barrel is a stark, honestly almost violent chemical divide. Right in the very center surrounding that incredibly hot white dwarf star, we have the hot ionized void. The gas here is just getting hammered by intense radiation, stripping electrons, ionizing elements like helium and oxygen, and driving temperatures up to a scorching 10,000 Kelvin. But, and here's the crazy part, right outside that void, making up the literal walls of our barrel, we find the exact opposite: dense rings of cold, neutral clumps. Out here, molecular hydrogen and carbon monoxide are surviving at a freezing 100 Kelvin. It is a spectacular contrast. You have this core of burning, highly ionized plasma completely and totally enveloped by a dense, freezing molecular shell.
Section 3. The cosmic lava lamp. Let's talk about fluid dynamics in space.
Now, this sharp chemical divide brings up a really compelling question. How exactly did this dense ring of cold molecular material fragment into the tens of thousands of individual clumps we see today? Well, the answer comes down to fluid dynamics. Specifically, a phenomenon known as the Rayleigh-Taylor, or RT, instability. This is an instability that triggers when a lower-density fluid pushes against a higher-density fluid, forming these distinct finger-like protrusions. Honestly, if you've ever watched the mesmerizing, splitting blobs of a lava lamp sitting on a desk, you have witnessed the exact same physics that sculpted the Helix Nebula.
Let's actually walk through this cosmic lava lamp step by step. Step 1 is the interaction of densities. Like we just talked about, the incredibly hot, low-density ionized gas from the center pushes outward against the cold, high-density neutral gas of the outer ring. Step 2 is effective gravitation and acceleration. The ionized gas is essentially acting as an exhaust, pushing outward from the central star in what scientists call the rocket effect. This intense outward acceleration acts just like gravity does in our lava lamp analogy. And this brilliantly illustrates Step 3, the formation of protrusions. The dense, cold gas resists this push, which causes tiny little ripples to amplify into long, finger-like structures protruding right into the hot void. Eventually, the shear forces pinch these fingers off entirely, leaving behind individual self-contained globs of dense gas floating out there.
Move into Section 4, a swarm of cometary knots, the cosmic tadpoles.
Zooming all the way down into the micro level of the nebula, through infrared data, just wow. This is exactly what happens when those finger-like protrusions pinch off. You are looking at a literal firework of dense molecular hydrogen cometary knots. I mean, they look like a massive swarm of glowing cosmic tadpoles, all seemingly fleeing from the central star off to the left. The scale of this alone is just breathtaking. But remember, we are only looking at a tiny fraction of the nebula's inner ring here.
As we noted right at the top of the explainer, current estimates suggest there are anywhere from 20,000 to 30,000 of these highly dense cometary knots populating just this inner region. And they are dense, packing up to 1 million particles per cubic centimeter. The anatomy of a single knot is super fascinating too. Each one features a bright crescent-shaped cusp, or head, that directly faces the intense withering radiation of the central star. But behind that glowing head, protected in a self-shielded freezing shadow, is a trailing tail of molecular gas pointing directly away from the radiation source.
Now, what's really interesting is how chaotic this process actually is in reality. When we zoom in even further, examining the various morphological shapes, we realize these knots are definitely not uniform, perfect little tadpoles. We see incredible fractured variations. Some of the tails are widening out, while others are narrowing down to a really fine point. Some have meandering, almost zigzagging tails, and others feature these complex multi-peaks, almost looking as if they've been shattered into pieces. This structural chaos tells us a much deeper story. These dense knots are actively being overrun and sculpted by high-velocity stellar winds, relentlessly photoevaporating the material right out into the void.
Which brings us to our final, provocative thought for today. We know the molecular hydrogen gas inside these knots is incredibly tough. I mean, it has survived since the star's earlier evolutionary phases. But as these dense molecular knots are slowly photoevaporated by the dying central star, what will these surviving cosmic tadpoles mean for the future interstellar medium? Will these clumps drift completely out of the nebula, seeding the galaxy with complex, carbon-rich molecules that will eventually form entirely new stellar systems? The Helix Nebula isn't just a beautiful graveyard, it might just be the very engine of future cosmic life. And that is absolutely something truly worth thinking about.